Design patterns and reference architectures are really just other people's production outages packaged up as diagrams so you don't have to repeat them. Hi, I'm Afzal from Confluent, and I've spent a good chunk of my career building and operating data pipelines. And in this video, I want to walk through the 3 data engineering architectures that keep coming up. We'll look at where most of us started, what we ended up building when the requirements changed, and where we should be trying to get to. Before we get into the nitty-gritty of the architectures themselves, let's agree on a simple mental model that we can use to evaluate all of them. Strip away all the vendor names and buzzwords for a second. Whether we're moving petabytes once a month or gigabytes every second, every data pipeline we build is effectively a directed graph. We have sources, where the data comes in, databases, Kafka topics. We have transformations, the business logic, filtering, aggregating, deduplicating, enriching, and many more. And finally, we have sinks, where the transformed data actually lands. These could be data lakes, analytics dashboards, or even back into another Kafka topic for downstream apps. Source, transform, sink. This model is universal. It doesn't care whether we're doing batch or streaming. This is what we'll use as a lens for everything that follows. Most of us start here. We've got our batch pipeline, sources, transformation jobs running in Spark or Snowflake, and one or more sinks. Since everything runs in batches, we need an orchestrator to decide when to kick off which jobs. Something like Airflow or Daxter or Argo workflows. Life is good. The pipeline runs, reports get generated, everyone is happy. Until someone in leadership asks, can I get this dashboard with real-time data? Now let's assume that the source data is actually available as a live stream. And let's also assume that you can't just run the batch job faster. Maybe it's too heavy for that. So you've got a design decision to make. Redesign the whole thing from scratch or patch what you have. In my experience, we almost always patch. We tell ourselves it's the pragmatic choice, and honestly, it usually is. So we add a second pipeline. We spin up an Apache Kafka topic, wire up some Apache Flink or Apache Spark streaming jobs, and now we've got real-time data flowing alongside our batch. Unlike the batch side, there's no scheduler needed here. The data just flows continuously. Then we build a serving layer to stitch the two views together, and now we have the 2 pipelines. One for the batch data coming in, and one for streaming. Congratulations! We've just built ourselves a Lambda architecture. A batch layer for long-term historical data, and a speed layer for the real-time deltas. It works. It powers massive companies. But having operated many of these, I can tell you it comes with a serious operational tax. In production, it's a headache, and here's why. Someone inevitably asks, why does the real-time dashboard show different revenue for last week than the weekly report? Sounds simple, right? To answer it, we need to figure out where the data diverged, and in a Lambda architecture, that means digging through 2 pipelines, which usually means 2 completely different tech stacks, often 2 different teams, the big data team and the streaming team. And here's the killer. The business logic is implemented in 2 places. Once in Spark or Snowflake for the batch side, and again in Flink or a custom Java app for the stream. Even if both sides happen to use SQL, the engines are different, the semantics are different, and the failure modes are also usually different. So when those numbers don't match, and that's going to happen, we spend our days having to debug both pipelines. I've been in enough of these postmortems to know that eventual consistency in a Lambda architecture usually just means it's inconsistent until someone manually fixes it. So if Lambda is what we end up with when we patch batch with streaming, and it comes with all this package, what's the alternative? This is where our next architecture comes in, and the core insight is beautifully simple. Batch is just a special case of streaming. Let me explain. An unbounded stream has a start, but no end. That's our standard stream of data, events flowing continuously. A bounded stream has a start and an end. In other words, it's a batch. If our processing engine can handle both, we can treat batch as just streaming, but with a finish line, and use one engine for everything. And that's exactly what the Kappa architecture does. We treat everything as a stream. Databases come in via CDC connectors like Debezium, logs via agents, external systems via their own source connectors, all flowing into a single unified stream in a broker like Apache Kafka. We use one processing engine, Flink in our case, to transform this data and send it downstream to other streaming clients, or even write it out to a lakehouse in some open table format. The result? One code base, one tech stack, which means one team with one set of skills. And most importantly, all the business logic lives in one place to debug, one place to change the business rules as they evolve. That's a massive reduction in both architectural as well as operational complexity. Now, whenever I talk about Kappa with teams, I get pushback. And it's usually the same set of concerns. One is, I can't afford to keep terabytes in my broker. This was a fair concern when streaming data had to live on the broker's local drives, but with tiered storage, KIP 405 shipped sometime in 2023, we can scale that out to cheap object storage. Another one is, how do my analysts query the data in the stream? Well, Flink SQL, Spark Structured Streaming, there are engines that let analysts write SQL against streams directly. No code required, and notebooks work against these streams quite easily. I want to use Snowflake or Trino or my favorite query tool against this data. Now, this is an interesting one and a valid concern because many tools cannot natively read Kafka streams. And if the data is large, replaying an entire stream to get to a specific bit of data could actually take some time. So let's look at what a practical Kappa architecture looks like and how it addresses these sorts of concerns. This is my favorite architecture, and you'll see why in a moment. Let's say we have a stream being consumed by multiple clients, and each one of them is doing their own transformations on the data. Suppose they're all deduplicating. Duplicating work to deduplicate? It sounds funny, but every data engineer knows this pain. So the first thing we do is shift left. We move our deduplication logic upstream, so we only do it once and provide the deduplicated data to each of the clients. This applies to any transforms, not just deduplication. The key is that the data gets cleaned before it lands anywhere. We all know how much cheaper it is to fix data quality at the source versus chasing it down in the warehouse after the fact. It's not just a matter of moving the transform upstream. Shift left also moves governance, schema enforcement, and data contracts upstream into the stream itself. Clients can now easily find and consume curated datasets. Second, we sync the stream into an open table format like Apache Iceberg or Delta Lake. Technologies like Tableflow make this straightforward. The stream just materializes as a table. Put these two ideas together and we get our third architecture, the data streaming platform. Now our clients get to pick their object storage and their query engine of choice. The data is available as a real-time stream for Flink or downstream microservices, and simultaneously as a high-performance Iceberg table for Snowflake, Spark, or Trino. Everyone gets what they need from the same data without us having to build separate pipelines for each of them. So there we go. 3 data engineering architectures. Lambda is what we end up with when we bolt streaming onto an existing batch system. It works, but we pay for it in operational complexity. Kappa unifies the processing into a single engine, but teams worry about historical storage and large-scale queries. The data streaming platform gives us the best of both, a streaming core that feeds both real-time apps and analytical warehouses from the same data. If you're designing a new system, aim for that unification. It saves money, it saves sanity, and it lets you focus on the data instead of the plumbing. I'm Afzal from Confluent. Thanks for watching.